So we are ready now to start with chemical equations and applying the concept of the mole. Let us start again with, say that this is a chemical equation. What this equation really tells us is that um, one particle of A reacts with a particle B, and to produce one particle of C and one particle of D. But because chemical reactions occur not in particles but in much larger numbers, we said that this equation can also tell us that 1 mole of A reacts with 1 mole of B to produce 1 mole of C and 1 mole of D. It so happens that in this general equation, the coefficients are all 1. So why 1 mole? Because we know that 1 mole of anything has exactly the same number of particles. So this can be single particles or could be 1 mole of particles, each of these. So in a chemical equation that represents a reaction, any statement about atomic ratios in equations or even informally are statements about mole ratios, really. And here now we have a real equation of a chemical reaction. We have calcium carbonate reacting with hydrogen chloride, perhaps it's hydrogen. What is this? This acid. Oh God. To produce these 3 products: sodium chloride and carbon dioxide and water. Okay. Now, what do we have here? We can say that 1 mole of, this is balanced now, okay? I mean, I wrote it balanced so that we have it ready. We have here this coefficient of 2, which means now that 1 mole of calcium carbonate reacts with 2 moles of hydrogen chloride to produce 1 mole of calcium chloride and 1 mole of carbon dioxide plus 1 mole of water, 1 mole. And it's not only in terms of moles. If we have a fraction of a mole, say if we had half a mole of calcium carbonate, if this was only half a mole, then this would react with only 1 mole of hydrogen chloride. In other words, half of this. So we need to maintain the correct proportions between the reactants and the products. So if we continue here, if we have half a mole of calcium carbonate, this would produce now half a mole of calcium chloride and half a mole of carbon dioxide and half a mole of water. And the same would apply if we had an even smaller, a fraction of a mole, a smaller fraction of a mole, say 0.1 moles of calcium carbonate. This would react with 0.2 moles of hydrogen chloride, and the rest would be also 0.1, 0.1, 0.1, and so on. So whatever, as long as we maintain the ratio which is determined by the coefficients of the chemical reactions, we are fine. And now these are very important for us when we try to find how many quantities that we need or amounts that we need in a chemical reaction to. And the moral of the story is that the idea of the mole, the concept of the mole, allows us to count particles by simply weighing them, having a scale and weighing amounts. And by knowing the amounts in the correct proportions, we are actually knowing, what we know is actually how many particles are participating. So from now on, we're going to talk about moles, of course, and the different fractions of moles that are involved in equations. Now, before we start with a problem that we need to apply to change moles into grams, in other words, changing amounts into quantities by mass and so on, let us see something else interesting here, since we have this chemical reaction, in which case whatever we said up to now about these fractions, these proportions that have to be maintained, is really what we are really applying here is the law of conservation of mass. Mass has to be conserved in a chemical reaction. And in fact, if we write if we convert each of these moles involved here, the quantities of the number of moles involved in this equation, and we change them into mass in grams, we are going to see that the mass of the reactants equals to the mass of the products, always in a chemical reaction, if it is correct. So the mass of the reactants is always equal to the mass of the products. And let us see that, let us convert these moles into grams here, because remember we said that the amount of 1 mole of a substance is numerically equal to the relative formula mass of this substance expressed in grams. You remember that when say this is the formula mass or the molecular mass of whatever substances are involved here, this number, this numerical value, if we express it in grams, this would be equal to 1 mole of this substance. So let us convert all those moles into quantities in grams. 1 mole of calcium carbonate, let's find first its relative formula mass of the calcium carbonate. I hope we remember how to do that. The calcium, let me check. I hope you remember me if I check my periodic table here. Where is calcium? Calcium is, we'll take it as 40. So this would be 40 plus the carbon is 12. Well, we have 1 atom of carbon, and we have 3 atoms of oxygen, each one with 16. And this should give us now, what is this? Should give us about 100, if I remember correctly. I remember it by heart. Should give us 100. 30. So yeah, this should be 100. So this number now, which is the relative formula mass of calcium carbonate, if we express it in grams, if we have 100 grams, this would be equal to 1 mole of calcium carbonate, So this is, if this is 100 grams, and what would be 2 moles of hydrogen chloride, or the relative molecular mass of hydrogen chloride. Hydrogen is 1, and what is 1? Doesn't write. And chlorine is 35,5, isn't it? Chlorine 35,5. Is altogether 36,5. So 1 mole of hydrogen chloride is 36,5 grams. And here we have 2 of these. 2 times 36,5 grams. Okay, so 100 plus 2 times 36,5. Altogether, if we add this together, 100 plus 2 times 36,5, this is equal to 173 grams. And if we do the same with the moles appearing in the other, in the right-hand side, calcium chloride plus whatever, we should also find 173 grams. Let's see, do we find 173? Now, the calcium chloride, for calcium chloride, the calcium we said was 40, isn't it? 40 plus 2 chlorine atoms, which is 35,5 each. This is 70, 110, isn't it? Check my calculations, guys. All right, and the carbon dioxide, relative molecular mass, carbon is 12. Oh. We need space. Okay, what is this now? Carbon dioxide. Okay, so that is 12 plus 2 oxygens, which is 16 each. 2, 46, isn't it? I hope. And the water, relative molecular mass of water, that is 2 plus, 2 hydrogens, that is, plus an oxygen, which is 18. And all this, if we add them together, 6 and 8. Do I have it right there? So, sorry, this is 111. Let me check my 44 here, not 46. And this is 18, and altogether should give us 173. Okay, so 18 plus 44 plus 111 is 173 grams. So you see, 173 grams on the left-hand side, 173 grams on the right-hand side. Yeah, thank you, 44. Yeah. Thanks, Adrian. All right, so we see that conservation of mass, the law of conservation of mass is observed here. So obviously, all right. That's enough with that. Now let us, let's see. Let's start with an easy problem. Let's start with this one, which is, I think it's in the book. I think this is the one, isn't it? Yeah, it's on page 163. It says here, let's see. What mass of aluminium oxide, why my pen doesn't write? Is produced when 9,2 grams of aluminium metal, so we have 9,2 grams of aluminium metal, reacts completely with oxygen gas. So we have 9,2 grams of aluminium metal reacting with oxygen to produce this aluminium oxide, and we need to find the mass of aluminium oxide. Okay. So let us see with the moles now what's happening. We have 4 moles of aluminium, reacting with 3 moles of oxygen, and the product is 2 moles of aluminium oxide. Okay. Now, what we need to do now, because we need to think in terms of moles here, we need to convert this 9,2 grams of that we have of aluminium into, we need to find how many moles of aluminium it represents. So the relative atomic mass of aluminium, the relative atomic mass of aluminium is, where is aluminium in the periodic table? Aluminium. It's 27. 27, I can't see properly. What do they say in the book? 27, yeah. All right, so this is 27, which means 27 grams of aluminium is 1 mole, not equal, but represents 1 mole, okay? Is 1 mole. In our case that we have 9,2 grams. We have 9,2 grams. How many moles is that? So we can take this ratio here and we can solve for x. It's nice to know how to produce this simple ratio. It will help us a lot. Okay, I hope you are familiar with these ratios, otherwise you'll practice now. So remember, 27 grams of aluminium is 1 mole. 9,2 grams that we have, how many moles is that? And we take the ratio. This is the ratio. So from here, we can solve for x. It's 27 over 9,2 equals to 1 over x. So from here, if we solve for x, what do we have? We have 1 mole times 9,2 divided by 27. You see now our answer will come out in moles. So this is equal to, I don't know, how much is that? 9,2 divided by 27, 0,34. So this is 0,34 moles. In that, which means now what? That the 9,2 grams here are actually 0,34 moles. 0,34 moles. So instead of having grams here, we can write it with the ratios of moles, 0,34 moles of aluminum we have. Now remember that the ratio is 4 to 3. Sorry, we don't care about the oxygen, we care about this. We need to find the mass of aluminum oxide, isn't it? So you see, if 0,34 moles of aluminum react, they produce half of the amount. You see, we have 4 to 2. The ratio is 4 aluminum to 2 aluminum oxide particles or moles or whatever. So the 0,34 mole here will produce half of this amount of aluminum oxide, because 2 is half of 4, isn't it? So 0,34 divided by 2 is 0,1517, isn't it? Is that correct? 0,17 moles, yeah. All right. I hope you understand that. We need to follow the ratios given by, we are guided by the equation, by the ratios shown in the equation. 4 moles produces 2 moles of aluminum oxide. So 0,34 moles will produce 0,17 moles of aluminum oxide. I hope it's understood. Okay, so now that we have the moles, the correct moles, now if we change the moles of aluminum oxide into grams, we find the mass that we are asked to find. So now we have that, of course, now we have, next step is we also need to find the relative molecular mass of aluminum oxide. So that the relative molecular mass of aluminum oxide is 2 aluminum, again the aluminum, what was that, 27, I think. 27 plus 3 oxygens, and its oxygen is 16. And how much is that? Should I do it in the book? Aluminum. I can't see it. Where is that? It's 102, it says, 102. Okay, so this is the relative molecular mass of aluminum oxide, which means 1 mole of aluminum oxide. 1 mole of aluminum oxide is 102 grams. Okay. Now, so 1 mole of aluminum oxide is 102 grams. The 0,17 moles of aluminum oxide that we have in our case, how many grams is that? And we take the ratio. You see, we'll always have to take this ratio, guys. I hope you, these ratios, hope your math is okay. So here, this ratio now, let's solve for x again. We can find the mass. So x is 102 grams times the inverse of that, which is 0,17 mole divided by 1 mole. Moles cancel. So this 102 times 0,17 gives us 17. I'm looking in the book. It says 17,3 grams. So there we found the mass of this aluminum oxide. Okay. So this is how we find it. Let us. Okay. So when they give us a mass, we change it into moles, and then we find moles, and then we change them back into mass, and we can find the masses that we are asked to find in a problem, well, provided that we are asked to find mass. I think the problems we're going to meet will involve masses. So we need to be careful how to make sure that we understand how to convert moles into mass and mass into moles. And I'm telling you this simple ratio, I suggest that you know how to work it out. So now let us see another example. Okay, we can do this one. All right, let's try this one. Let me read you the problem. Let me find the problem. Yeah, okay. This problem says, what mass of sodium chloride, must be used to complete the following reaction, which is this one, if we start with 1,7 grams of silver nitrate. If we start with 1,7 grams of silver nitrate. Okay, if we have 1,7 grams, how much, what mass of sodium chloride do we need? In other words, we need to weigh how much sodium chloride we're going to need. And therefore, we need to convert again, we need to talk in terms of moles again. First of all, is this equation balanced? It is balanced. 1, 1, 1, 1. Correct. 1 of this nitrate. Yeah, it's balanced. All the coefficients are 1. That's great. So we see that 1 mole of silver nitrate reacts with 1 mole of sodium chloride to produce 1 mole of this and 1 mole of that. Sodium nitrate and silver chloride. Great. Now, next step is to find out how many moles does this given mass represent. So, which means now we have to find the relative formula mass of silver nitrate. So, for silver nitrate, I hope I have it. Do I have it? Yeah, great. Silver nitrate, where is the silver nitrate? Yeah, great. I have, let me give you here what I find here. 107, oh dear, I use decimals. I'll make it 108. 108 for silver. For silver, yeah, let's use it as 108. It's relative atomic mass. The nitrogen is 14, and the 3 oxygens, 3 times 16. Altogether, I find I'll make it 167. Sorry, 170. 170. 170. Dear me. I can't avoid messing up, isn't it? 170. All right. Grams per mole. Which means that 1 mole of sodium, what is this, silver nitrate is 170 grams. So 1 mole of silver nitrate is 170 grams. The 1,7 grams that we have, how many moles is that? And of course, here is the ratio, but we can see straight away that the 1,7 is the is 0,1 here, isn't it? The X will be 0,1 moles. Okay. 0,01, sorry. Okay, so there's 1,7 grams of silver nitrate actually is 0,01 moles. So now if we follow now the ratios shown by our equations, we have 1 to 1 to 1 to 1. All of them are 1 to 1. So if we have now 0,01 mole of silver nitrate, it will react with 0,01 moles of sodium chloride, and it will produce 0,01 moles of this and 0,01 mole of that. All right. Now we are interested in we want to find the mass of sodium chloride, and therefore Now we have the moles of sodium chloride necessary. What mass must we weigh to have the 0.01 moles of sodium chloride? Again, now we need to find the molar, well, the formula mass of the relative formula mass of sodium chloride, which is the sodium is sorry, what is sodium? 23 plus, and I think chlorine is 35.5. And sorry, and the result is 23, 88, 58, I mean 58.5. Okay, which means now that 1 mole of sodium chloride has a mass of 58.5 grams. The 0.01 moles that we have available in our case, how many grams does this represent? And we take the ratio and we solve for x, and this is 58.5 grams times 0.01 mole divided by 1. Okay, so here that will be 0.58, yeah? 0.58, yeah, that's enough. There's no need to have more figures. Grams. So this is the mass that we found. This is the mass of sodium chloride. So this is 0.58 grams that we found. So 1.7 grams react with 0.58 grams, because both of these quantities represent 0.01 mole according to this equation. Okay. Okay. People, do this make sense to you? Will you manage to do this ratio every time we need it? Please let me know. You send me a message quickly, because we are not going to start a new problem now because we have 2 minutes left. And if you want, we can do a couple of problems more next week. Please let me know. I'm waiting for your message. We can also talk about the yield and so on, percentage yield. Okay. Let me know if you need to, should we do a couple more problems next week? All right, in this case, okay, let's stop sharing. All right. So next week again, we can take it a step further. All right. So keep well, guys.